Hello and welcome back to my lecture series on James space, a counterexample from functional analysis, or more precisely, Banach space theory. In this video, we will prove the central theorem of this lecture series, which is that James space J has a monotone shrinking basis. And this basis will be En. This is En. And we will have that alpha n will just be the sum of the alpha n's times the en's. And these en's, this is the standard basis that we also know from C0. So E1 has a 1 at the first index, and E9 has a 1 at the 9th index, and it's only zeros in the other places. So this will be one hell of a proof. And we will begin with the following remark, that if we have an alpha n and j, then every finite subsequence of alpha 1 up to alpha k for some integer k, and then only zeros, is also a finite subsequence of alpha 1 up to alpha k plus 1, and then only zeros. And it follows from that the norm of this vector right here, the A norm, the James space norm, is less than or equal to the norm of this vector here, where we add one more dimension. And what does this tell us? This tells us that En is a monotone basic sequence. Now, this was corollary 1.13, the small Greenblum criterion, as I like to call it. Now, what do we need? We now need that J is spanned in its entirety by these En's. That's what we want. So then En is also a basis. So let alpha n be in J. What do we want to show? We want to show that this representation here, alpha n En, this representation here, this should converge to alpha n. So we want to show that this, which can also be written as this, alpha k plus 2, this should converge to 0 as k goes to infinity. And we will prove this by contradiction. So assume this is false. Then there exists an epsilon greater than 0, and for every j from the natural numbers, there are indices Pn, and I will add a second index at the top. Now this will be indices from our set F that we defined earlier, such that they come after another. So the last element of the jth indices, this is smaller than the first one of the j plus 1 indices. And this goes for all j. And another property that they fulfill, which we just get from this observation, is that this sum right here, alpha p j n minus alpha p j n plus 1 squared plus alpha p m j j alpha p 1 j squared, this is bigger or equal to epsilon, right? Because if, as we assumed, this right here doesn't converge to 0, then there must be, at any point in the series, doesn't matter how far in we look for them, there must be indices who push the norm over this minimum, so to say, epsilon. And due to the definition of the norm, they thus must fulfill this inequality. And now we can juggle around with this a bit. We can bring this over here, and then we get that this sum right here p n j minus alpha p n plus 1 j squared is bigger or equal to epsilon minus alpha p m j j squared minus alpha p 1 j squared. Now we can make these two arbitrarily small because alpha n is a zero sequence. So there is a j in the natural numbers, a j0 in the natural numbers, such that for all j greater or equal to j0, we have that this gets smaller than epsilon fourth. So we get that this sum right here, alpha p n j minus alpha p n plus 1 j squared, is actually bigger or equal to epsilon minus epsilon quarter minus epsilon quarters. So this is greater or equal epsilon half. And now we let t be a positive integer and j greater or equal to j0. Then we define that q and t, again, this is a index, this is a sequence in n, will be, well, we just add these pn's that we have here, these pn's here, we will put them after another. Because we have this property, we just line them all up. So we begin with the first element of the jth sequence. We go all the way to the last element of the jth sequence. And then we bring the first element of the j plus 1th sequence all the way to the last element of the j plus 1th sequence. And we will do this again and again up until the very last element of the very last sequence, and the last sequence shall be the j plus tth sequence. That's what we got this t here for. So this will be pm j plus t, and this will also be j plus t. This is an element of f, obviously, and with this inequality right here, with this inequality, we get that z of alpha, q, and t, this is greater or equal to t times epsilon half, and this obviously diverges as t goes to infinity. Thus, the norm of alpha n is infinite. But that's a contradiction because alpha n was an element of J. So what we get is that indeed the closed linear hull of these ENs is all of J. So En is a monotone basis. What remains to be shown is that En is shrinking. So here as well, we want to assume that the contrary is true. Assume En is not shrinking. And this is the hard part. Then the coordinate functionals are not a basis of the dual space of J, because that is equivalent to being a shrinking basis. So there exists a functional with norm 1 which is not part of the closed linear hull of these coordinate functionals. So this sum right here does not converge to x dash. However, with theorem 1.15, we know that x star is actually the weak star limit. X dash is actually the weak star limit of this sum right here. So this means that the sum does not converge to any other functional, because then the weak star limit would also be that functional. But the weak star limit is x dash. So what we conclude is that this sum is divergent. So what does it mean that this sum is divergent? This means that there exists a delta greater than 0 and natural numbers q1 shall be 1 and this shall be less than q2 and less than q3 and so on, such that the norm of the sum with n starting at qk and going up to qk plus 1 minus 1 of x dash of En times En dash in the norm on the dual space, so on the J dash norm, is greater or equal to delta for all k in N. And if we remember the definition of this functional norm, we know that for all k from the positive natural numbers, we will find an xk in J, so a vector, with norm 1 such that if we apply this functional qk plus 1 minus 1, if we apply this functional to xk, and we can write it like this because of linearity. This must be greater or equal to delta. Now we define yk to be the sum n starts at qk and goes up to qk plus 1 minus 1 of en dash of xk times en. And these yks are a block basic sequence. And if you don't remember that, go check out definition 1.19. It was in the third video of this lecture series. So these are a block basic sequence of En. And furthermore, if we put this yk into our functional, this is just greater or equal than delta, because then we get exactly this term right here. Now, we can also find a normalized block basic sequence, which we will call un of En, such that when we apply our functional, this will be greater than delta for some delta. This might be a different delta, and it probably is. But we can now also find one for a normalized block basic sequence. And this right here goes for all n. And then this sum diverges. So this is infinite. So this sum right here is divergent in J. So with respect to the norm that we decorate with this little a. So a divergent. And now, to achieve a contradiction, because we assumed the basis to not be shrinking, now we want a contradiction. To achieve this, we will show, we will show that there exists a real number greater than 0, such that the norm of this divergent sum when we only take the dimensions m1 to m2, and here we use the B norm, this will be less than C times this term right here. And this will be a contradiction, because if we let m1 be equal to 1 and then let m2 tend towards infinity, this right here will converge and this right here will diverge. And that's a contradiction because of this sign right here. Okay, so now we have our block basic sequence. So we know that we have real numbers zeta n, and we have numbers q1 less than q2 less than q3, and on and on and on, such that uj is the same as the sum going from qj up to qj plus 1 minus 1 zeta n en. And we also know that the norm of uj, the a norm, is 1. Great. Now, from this fact already, it follows that the absolute value of these zeta n's is always less than or equal to 1. So now let m1 and m2 be natural numbers with m1 less than m2, and let gamma n be the following sum. We go from m1 up to m2. We take j to the power of -1 times uj. Okay, and don't be confused. Here is an n, right? Why is there no n here? Well, that is because this is a sequence. And we call this sequence gamma n. So this n is not really standing for anything. It's just that this right here, this gamma n, is a sequence. This sum is a element of j, and so is gamma n. Okay. Now we fix some indices p1 to pm from f, and we will want to consider the following sum. S, and this will be the same as the sum, so n goes from 1 to m minus 1 of gamma pn minus gamma pn plus 1 squared. So this is very convoluted. We have here a sum of elements gamma n, which are then again defined as a sum. So gamma n is defined as a sum of uj's, which are also again defined as a sum. But we will slowly unravel this. Now, S is the sum of elements of the following set C, which will be, well, literally just the set of these summands right here, and n goes from 1 to m minus 1. But why do we do this? Well, we will now split this set of summands up, and thus split S up into two sums. We let C1 be the set of elements of C, so the set of summands gamma p k minus gamma p k plus 1 squared, such that pk and pk plus 1 belong to the same block uj. That means, that is, that there is a j element n with qj less than pk plus 1, and this is less than qj plus 1. Okay, so if you don't remember what this means, go check out again the definition 1.19 in the third video, at the end of the third video. And we also say C2 is the other summands. Okay. Then we set S1 to be the sum of elements of C1 and S2 to be the sum of elements of C2. And then we have S being equal to S1 plus S2. Look at S1. Now, as an example, the blocks of UN of our block basic sequence could look somewhat like this. So here we begin. This is our Q1. This is our Q2. This is our Q3. Then we have a Q4. And this will just go on. And maybe here we have P1 up to P3. And here we may have a P4 and a P5, and here maybe a P6 and a P7. So here in this example, the P1 and P3, they belong to U1 because U1 is made out of these factors right here. You will see it up here, right here, as going from Q1 to Q2 minus 1. So U1 is exactly this block right here. And these don't belong to the same block, right? And as such, we know we will sum over all these different blocks, but we will only sum the gamma pk's that are these differences. So we will only sum this difference and this difference. We will not sum this difference. However, we will again sum this difference. Okay? This means that we can write S1 in the following way. S1 is the sum, and now we here go over all the blocks of, and here we now take only those for which the pk and pk plus 1 belong to the same block, because that's exactly what we want in S1. So this is qj less than pk less than pk plus 1 less than qj plus 1. And over all of these indices k, we will then finally sum up gamma pk minus gamma pk plus 1 squared. Now another complication arises, because for every of these summons, gamma pk minus gamma pk plus 1 squared, we could have that pk and pk plus 1 belong to a uj where j is less than m1, or maybe j is greater than m2. And in that case, the summand is 0, because gamma is only made out of the blocks M1 to M2. So we go from the M1th block to the M2th block. However, our gamma pk might lie outside of that, outside of this range that actually has values, because obviously the series gamma n is still defined for every index n, right? But it's 0 outside of these blocks. So then this is just 0. It's 0 minus 0 squared. However, this doesn't have to be the case. Otherwise, we have that gamma pk minus gamma pk plus 1 squared. Well, what is this? This is the same as, first we will just put in what it means, what gamma means. This is the sum that defines gamma, n to the power of minus 1 times un. From this we take the pkth element, and then we also take the pk plus 1th element. And this all squared. Now, what is the pkth element of this sequence? Or the pk plus 1th element of this sequence? Well, we know that it is actually some value, and we know for a fact that they belong to the same block, uj. And this uj was defined in the following way. In this way. And the pkth element, we know, will lie in this range of gamma. So we will have zeta pk, and then this j to the power of negative 1. So this will be j to the power of negative 1 uj, and from that the pkth element. And here we have the same thing, but the pk plus 1th element. And this is the same as the j minus 1 times this sum right here. This is just the definition of uj, right? Zeta n en pk minus j to the power of negative 1. And here we have the same, qj up to qj plus 1 minus 1, zeta n en. And from this, the pk plus 1th element. That is just j to the power of negative 1 times zeta pk. And here we have j to the power of negative 1 times zeta pk plus 1. And this is the same as j to the power of negative 2 times zeta pk minus zeta pk plus 1 squared. Okay, this might be a bit hard to wrap your head around, but I hope it's somewhat clear when we do it in these steps. So here we only put, here in the first step, we only put in the gamma, and this is where the whole argument goes on. We just need to very sharply look at the sum to see that this step right here is true. And now with this identification, we can calculate, or not calculate, but find a nice inequality for our sum S1. So S1 is the same as, and this is what we wrote earlier, the sum of j going from 1 to m minus 1 of the sum of all these indices k, such that qj is less than pk, this is less than pk plus 1, and this is less than qj plus 1. And what do we sum? Still the gamma pk is minus gamma pk plus 1 squared. Now, this is the same with what we found out as the sum j going from 1 to m minus 1 of the sum of these indices right here of j to the power of negative 2 times zeta pk minus zeta pk plus 1 squared. Now we can pull this j to the front, and we can then use an inequality. We can make this bigger with taking the supremum of this over all possible finite subsequences pk. And we do this to get an inequality which uses the norm somehow. So this is the same as this sum. We take the j to the power of negative 2 to the front, and what remains will definitely be less than or equal to the supremum of this sum right here. We go from r equals to 1 up to t minus 1 of zeta sr minus zeta sr plus 1 squared, where s1 up to st are from our set F. Okay. And the nice thing now is that this is the same as the sum as j goes from 1 to m minus 1 of j to the power of negative 2 times 2 times the norm of uj squared. And it's the b norm because we dropped the cyclical summation. Okay? And since this is just 1, this is 2 times the sum as j goes from 1 to m minus 1 of j to the power of negative 2. And that's the inequality that we wanted for our S1. But it's not only S1, it's also S2. So next up we look at S2. Look at S2. We will fix a summand gamma pk minus gamma pk plus 1 squared from the set C2, which contains those summands such that pk and pk plus 1 don't belong to the same block. And we let uj1 and uj2 be the blocks that pk and pk plus 1 belong to, respectively. And as before, either gamma pk is equal to 0 or gamma pk is equal to j1 to the power of negative 1 times zeta pk. And the same goes for gamma pk plus 1. Gamma pk plus 1 is 0 or gamma pk plus 1 is equal to j2 to the power of negative 1 times zeta pk plus 1. It's the same argument that we used up here, where we had the where we considered different cases, and then we got, well, these values for gamma pk, this one for gamma pk plus 1. So anyway, let's continue. We get that gamma pk minus gamma pk plus 1 squared, well, this is equal to gamma pk squared minus 2 times gamma pk plus 1 plus gamma pk plus 1 squared. We know that from school. This is less than or equal to j1 to the power of negative 1 times zeta pk squared plus j2 to the power of negative 1 zeta pk plus 1 squared. So this is our gamma pk plus 1 squared plus 2 times, and now we will juggle around a bit. This is the two j factors that are in front, and then we will use the absolute value of the zetas. So we know that this is for sure less than or equal to. Great. And at the very beginning, we found out that the absolute value of the zeta pk's, or of every zeta, is less than or equal to 1. So with another inequality, we can drop all of those. We get j1 to the power of -2 plus j2 to the power of -2. And what remains here is 2 times j1 to the power of -1 and j2 to the power of -1. And this is less than or equal to j1 to the power of -2 times j2 to the power of -2 plus j1 to the power of -2 plus j2 to the power of -2, which is just 2 times j1 to the power of -2 plus 2 times j2 to the power of -2. And if we repeat this argument for all the summands from C2, we see that every factor j, which is between m1 and m2, can appear at most once as j1 and at most once as j2. Yeah, we will have something that looks kind of like this. And then the next summand might look like this. And then the next summand might look like this. And so on and so on. So what we can conclude from that is that S2 is less than or equal to the sum, as j goes from m1 to m2, of 2 times 2j to the power of -2. And this is just 4 times the sum, as n goes from m1 to m2, of j to the power of -2. In total, we get that 1 over the square root of 2 times this sum right here, gamma pn minus gamma pn plus 1 squared, all in the square root. We can rewrite this. This is the same as 1/2 times s1 plus s2. And we found our nice inequalities. So this is less than or equal to 1/2 of 2 times the sum of n going from m1 to m2 of n to the power of -2 plus 4 times exactly the same sum. So n to the power of -2 is all in the square root. And if you calculate this, this is the same as square root of 3 times the sum, as n goes from m1 to m2 of n to the power of -2, and all in the square root. Okay. And as noted, we get that the B norm of this sum is less than or equal to square root of 3 times this sum. And this is the C that we wanted, the C which is greater than 0. And this inequality holds because, well, of this thing here that we found out. So this is our contradiction, because for m1 equal to 1 and m2 going to infinity, we have that, well, how do I write this? This thing diverges, and this thing right here, it converges, and it actually converges to pi over square root of 2. Isn't that a beautiful number? Well, whatever. It's what we wanted. We get that En is shrinking. And we are finally done with this mega proof of this central theorem. And in the next lecture, we will prove the exciting properties that make studying James space so interesting. Until then, goodbye.